Before I want to talk about dielectrics too much, I want to remind you of a couple things about capacitors, because dielectrics are essentially insulators that you put inside, in between the two plates of a capacitor. So, if you've got a capacitor, the capacitance of the capacitor is the ratio of how much charge you can store on it divided by what voltage, what potential difference you had to put in between the two plates of the capacitor. And so a capacitor is basically a mechanism that we can create to store charge using a potential difference. So we're storing charge, or equivalently, we're actually storing energy. And the energy that's stored inside a capacitor is going to be 1/2 the voltage you had to put between the plates times the charge you're able to fit onto that plate. So that's what's going on with capacitors. Let's see how a dielectric helps the capacitor get better at its job of storing charge, by which we mean really it's storing energy for us. So say we've got a capacitor and there's no dielectric in it yet. It could be any sort of capacitor, but I'm going to draw a parallel plate capacitor because that is just simply easier for us to think about. And I am going to attach a battery to the two plates of this capacitor. This is the positive side of the battery, that's the negative side, and that's going to put a voltage. I'm going to call it V0 because this is going to be the capacitor before I've stuck the dielectric in. Alright, so then once I hook this battery up, what's going to happen is I'm going to start getting negative charge accumulating on this plate, the one that's attached to the negative side of the battery, and then I'll get an equal amount of positive charge accumulating on this top plate that is attached to the positive side of the battery. And the charge is going to keep flowing onto these two plates, building up and building up until the potential difference between the two plates of the capacitor is V0, the same as it is on the battery. And of course, that's happening because when I build up these charges, I'm also creating an electric field that goes from the positive charges to the negative charges. And remember that you get an electric field whenever you have a voltage built up and they're related by the gradient, or if you want to do it the other way, the potential is the integral of the electric field across a path. So we always walk negative plate to positive plate. That makes this potential difference positive just by definition. So that's what's going on with capacitor. Now let's say, oops, I forgot to also put on explicitly. We have some negative charge there, down here, negative charge on this side, positive charge on that side. Now what I'm going to do is I'm going to freeze the charges on the plate. They're not allowed to leave. And you can do that by disconnecting the battery. Then these charges, no matter what you do with the capacitor now, they can't escape off the capacitor. So the charge is going to stay the same. Now I'm going to put in a dielectric. So I'm messing up my electric field. I put in this insulating material inside here. There it is. So this pink stuff is my dielectric. And remember, it's an insulator, so it can't act like a conductor. It can't just like have little electrons running up here to meet the positive charges up here, even though of course they want to. There's a force on them from the electric field trying to get that to happen. But the dielectric, that means all of the electrons are stuck in their atoms. However, an atom is, you know, the positive nucleus and then the negative electron, which is orbiting around in the cloud. Even though the electron can't escape and travel up here, the whole atom itself can become polarized. So basically, the negative electron is going to get pulled upwards toward these positive charge, and the positive nucleus will be attracted down here to the negative charge. So all the atoms in this dielectric are going to get polarized. And the net effect there will be like, well, right here we'll have a little atom, and it'll have its electron up there, and its nucleus down there. The next atom over is going to have its electron attracted up, and its nucleus attracted down. And then so forth and so on, until what you're going to get is essentially a negative charge up here and a positive charge down there. And in between, you'll have these little paired negative and positive charges from different atoms, but they're still paired, so they cancel each other out. And this is going to happen all over the dielectric. So you're going to get a little bit of negative charge up here by the positive plate, a little bit of positive charge down here by the negative plate. Now it can't change this charge because it has to stay in the dielectric. It's not allowed to hop onto the metal plate. But overall, what that's going to do is that's going to reduce the electric field. Because now, if I draw it, the electric field is going to be like that, much smaller, because there's less sort of net charge up here. It's these blue positive charges on the conductor, and then also these pink negative charges in the dielectric. So overall, the net charge up here is smaller than it has been, even though the charge on the capacitive plate hasn't changed. Let me actually go ahead and dry this electric field in pink because it's inside the dielectric. And so that means the electric field in the dielectric is going to be smaller than it was when it was without the dielectric, than it was originally. And because the electric field's smaller, that also means the potential is going to be smaller than it was originally. But the charge on the capacitor hasn't changed because we've disconnected the battery. There's nowhere for this blue charge to go. All right, so what is that going to do to the capacitance? Well, any dielectric material you have is going to have what is called a dielectric constant. And we use a kappa for it. And the dielectric constant, by definition, is what you need to multiply the electric field by when there's a dielectric to get whatever the original electric field was. Or in other words, you can divide the original electric field by the dielectric constant to get the electric field in the new material. And because kappa is a scalar and a constant, the vectors just keep working on. All right, a couple important things about this dielectric constant. K is a constant. It is always bigger than or equal to 1. If the dielectric constant is 1, that means you're in a vacuum. That is, you're actually not having any dielectric at all in there. Air is pretty close, so you can basically assume that kappa is pretty much 1 for air, but if you've got something like, I don't know, paper, which is a pretty good insulator, kappa's 4. If you've got, I don't know, something that we actually use for a dielectric, like barium, let's see if I can remember this. Barium titanate, I think that's the formula. Anyway, then kappa is on the order of 1,000 to 10,000, so quite big. So important thing for all of this is that K is always positive. And you also notice it doesn't have any units, which of course makes sense because the electric field units have to be the same, so kappa can't have any units. All right, so that's kappa. Knowing that kappa is always constant, always positive, that tells us that, yeah, the electric field is going to be smaller when you stick a dielectric in there than it was originally. The voltage is going to equally be smaller than the original voltage, but here, because we've disconnected the battery, the charge stays the same. So then when we look at the capacitance, well, originally, we had the original capacitance is the original charge over the original voltage. The new capacitance with the dielectric is the new charge over the new voltage, but the new charge is the same as the old charge. And the new voltage is 1 over kappa times the old voltage. And if we rearrange that, oops, should have done that Q in blue. If we rearrange this, we got 1 over kappa in the bottom, so we can move that up. Q naught over V naught. So K times our original capacitance, just we have here, and since K again, always bigger than 1, always positive, our new capacitance is bigger than our old capacitance, which means, since capacitance is the ability to store charge in the voltage, given a certain voltage, if you make the capacitance bigger, we can store more charge, and we can also store more energy. Now you'll notice that's not actually what happened in this situation. And that's because we disconnected the battery. So let's actually redo this for what really goes on in a capacitor. Usually you have your capacitor like this, and it's empty, no dielectric yet. We'd attach it to the battery. So negative on this side, positive on this side, whatever the voltage of the battery is, the charge goes onto the plates. Negative charge goes onto these plates, and we get a positive Q naught on this side, we get a negative Q naught on that side. The potential difference in here is V naught because we have created an electric field. And remember, if we know the potential difference, which we do because we've got the battery here, we necessarily know the electric field in here. So it's going to go positive charges to negative charges like this. All right, so that's the setup before we put the capacitance. Now, what we're going to do is we're going to leave the voltage battery connected, and that means that our new voltage is going to be the same as our old voltage. But we stick the capacitor in here. Sorry, we stick the dielectric in here. There it is. Same thing's going to happen as what happened before. We are going to get the atoms inside the dielectric going to polarize. We're going to get sort of a little bit of negative charge up by the positive plate, a little bit of positive charge down here by the negative plate. Can't perfectly cancel out the charge on the actual capacitance plate because dielectrics, the charges can't run freely. The atoms can just sort of stretch a little bit and polarize. But now, instead of what happened before, where we just weaken the electric field in here with these charges, well, the electric field has to stay the same because the voltage has to stay the same, and the voltage has to stay the same because it's still connected to a battery with this voltage. So what's actually going to happen is more charge is going to come on the plates. So we're going to get an additional plus charge on the plates for every little negative charge here that's in the dielectric, and then down here we'll get an additional negative charge on the plates. Let me actually draw it on the plates. For every positive charge that's in the dielectric. So our new charge with the dielectric is going to be bigger than our old charge. And then down here, I guess to make it not as confusing, I'll put absolute values around that. The new negative charge down here is going to have a bigger magnitude than the old negative charge down here. So the charge increases. So yeah, the capacitor now is storing more charge for the same voltage. So it has a bigger capacitance. And it's going to be same ratio as before. It's going to be the old capacitance multiplied by kappa, our dielectric constant. The voltage, because it's still hooked up to the battery, is the same voltage. But the charge has increased. And how much has it increased for? Well, let's take a look at this equation. We've got our capacitance is the charge over the voltage. The voltage hasn't changed, but the capacitance has increased by K. Let me just take this, and C naught, well, that is the old charge over the old voltage, and so looking at this, we can see that the new charge has to be the old charge times kappa. So the new charge is bigger than the old charge by this amount, kappa, which is exactly what we see going on here. And because the charge is increased, but the voltage has stayed the same, so V is the same, Q is bigger, our stored energy is also bigger. So the new stored energy is going to be the old stored energy multiplied by our dielectric constant. So that is how we use dielectrics, which are these insulating materials. So key thing, a dielectric is an insulator that we stick inside a capacitor, and because the insulator is going to polarize like this, it increases the capacitor's ability to store the charge or store energy for us. And I forgot to add, where does this extra energy come from? Because of course, energy's got to be conserved. That's one of the main sort of basis of all of physics. So the energy, this new increased energy, is coming, well, from the battery. Same as where the old energy came from. The battery is moving more charge onto the plates, which is creating more energy stored in this space because it's increasing the potential energy. And so this extra energy, well, we make the battery work a little harder, and then we can store more energy in here.